Hello everyone. Post-forming processes include heat treatments as drying and firing, as well as surface treatments as film printing and coating, and surface finishing or machining. Let's start with drying. Drying is the removal of liquid from a porous material by means of its transport and evaporation into a surrounding unsaturated gas. It may be applied to raw materials, dry route, slurry, spray drying, or, most commonly, to green bodies, post-forming prior to firing. Chamber dryers are used for drying large freestanding shapes and smaller products supported on shelves. Continuous dryers may convey the wear up and down by means of shelves supported on continuous chains in a tunnel dryer. The dryer may be operated with waste heat from the kiln, not requiring any additional burner. In a drying system, heat energy must be brought to the surface of the product. Liquid is transported through pores to the meniscus, where evaporation occurs, and vapors must be carried away. This plot shows the moisture content versus time. At zero time, the initial moisture content is at point A at a colder temperature. If the solid is hotter, it may start at point A line. Eventually, at point B, the surface temperature reaches equilibrium. From B to C, the line is straight, corresponding to a constant drying rate. At point C, the drying rate starts to decrease. At point D, it falls even more rapidly until it reaches point E, the equilibrium moisture content. Thus, the drying rate is strictly constant when the evaporation rate and evaporation surface area are constant. The distribution of liquid among particles during slow drying can be seen as cast, just preceding the end of the constant rate period, entering the falling rate period, and near the end of the falling rate period. The dependence of the volume of the piece on the liquid content for homogeneous drying, where the liquid content is spatially uniform, is shown here. Shrinkage ceases at a particular liquid content, which is called the critical moisture content. Warping is caused by stresses accompanying non-symmetrical shrinkage, and it's reduced by increasing the uniformity of drying. Differential shrinkage due to a differential liquid content when the product was formed or differential drying rate across the surface of the product may also produce warping. Now, we skip to heat and surface treatments. First, we're going to talk about coating processes. Vapor deposition is the condensation of an element or a compound from the vapor state, forming a thin film, typically less than 1 micrometer, on a substrate. In physical vapor deposition, the film has the same composition as the vapor. The most common PVD processes are sputtering and evaporation. In chemical vapor deposition, CVD, a compound of the source material is vaporized and thermally decomposed or reacted with other gases or vapors to produce a non-volatile reaction product which deposits onto the substrate as a thin coating. In screen printing, an open pattern in a stencil screen defines the printed pattern. A thick paste is forced through a stencil screen onto the surface below using a squeegee and nozzle assembly. Common screen-printed thick films are larger than 200 micrometers. Typical methods for glaze application are shown here. Many ceramic products are coated with a slurry which forms a partially vitreous coating when fired. Frit is a glass powder which on firing speeds the reaction and spreads the vitrifying coating. Other inorganic additives serve to develop the proper rheology and grain strength. This chapter presents the use of heat in a series of phenomena usually referred to as firing. Firing, in related terms in other languages, are related to the use of a fuel as a heat source, reminding combustion. Some other languages refer to this step as cooking or baking, which is related to the transformation of a material inside a furnace, kiln, or oven. Firing proceeds in three stages: reactions preliminary to sintering, which include organic burnout, sintering itself, and cooling. Ceramic materials and products are fired in a variety of kilns and furnaces that are designed to operate either intermittently or continuously. Furnace is a general term for an enclosed chamber in which heat is produced. The more specific term kiln is commonly used in the field of ceramics. Sintering is the term used to describe the consolidation of the product during firing. Consolidation implies that within the product, particles have joined together into an aggregate that has strength. The term sintering is often interpreted to imply that shrinkage and densification have occurred. Highly porous refractory insulation products may actually be less dense after they have been sintered. Sintering commonly occurs at 1/2 to 2/3 of the melting temperature in the case of a single component system. Material changes on heating prior to sintering may include drying, the vaporization of chemically combined water, the decomposition of organic additions, the pyrolysis of particulate organic materials, changes in the oxidation states of some transition metal and rare earth ions, and the decomposition of carbonates, sulfates, and so on. Thermolysis, debinding or organic burnout, is an important step prior to the densification on sintering. Incomplete binder removal and uncontrolled thermolysis may introduce a new population of product defects. Binder burnout is very dependent on the composition of the binder material and the composition and flow of the gas surrounding the product and in the pores of the product. The burnout of additives from an extruded and a tape cast green body is compared here. In the extruded sample, only a main peak can be seen at around 300 degrees C, corresponding to the combustion of the binder. In the cast tape, three main peaks are observed, respectively for dispersant, a plasticizer, and a binder, which are eliminated at increasing temperatures. In the case of clay-based ceramics, we notice the loss of water, both adsorbed and combined, at increasing temperatures, as well as the decomposition of kaolinite into metakaolin at temperatures before the sintering path is reached. Now we will present the most important heating step in the ceramic processing: sintering. Sintering is a high-temperature process that can develop in different ways, in a unique or combined manner. Solid-state sintering (SSS) occurs when pores are removed by diffusion between particles with no liquid present. Liquid phase sintering (LPS) is carried out when up to 20% liquid is present to enhance diffusion, mass transport, and rate of pore removal. Viscous composite sintering (VCS) or vitrification occurs when there is a mixture of liquid, more than 20%, and solid particles, such as for whiteware or clay-based ceramics. Viscose glass sintering (VGS) involves only liquid phase and is the mechanism in glazing and enameling. Respective examples of SSS, LPS, VCS, and VGS are given. SSS: alumina plus magnesia, zirconia plus yttria, silicon carbide plus boron carbide. LPS: silicon nitride plus yttria, silica, or alumina. VCS: porcelain. VGS: glazes. An example of the densification behavior by SSS of a dense compact of magnesia-doped alumina is shown here. The density increase of about 2% corresponding to the upturn of the curve is called the initial stage. The range of major densification, the intermediate stage, and the range of rapidly decreasing rate and cessation of densification, the final stage. In the case of conventional sintering, a residual porosity is observed. When hot pressing is applied, a relative density of 100% is reached. Microstructural changes in the stages of solid-state sintering are observed here. Initial: surface smoothing of particles, grain boundaries form, neck growth, rounding of interconnected open pores. Porosity decreases less than 12%. Intermediate: shrinkage of open pores intersecting grain boundaries. Mean porosity decreases significantly. Slow grain growth. Final: closed pores containing kiln gas form when density is about 90%. Closed pores intersect grain boundaries. Pores shrink to a limited size or disappear. A significant proportion of ceramic products used in low-temperature applications are predominantly crystalline materials containing a minor amount of a glassy phase, distributed in the grain boundaries. Typical stages for LPS are particle rearrangement, solution precipitation, and elimination of closed porosity. When the liquid coats each grain, the material may often be sintered to a higher density at a lower temperature with less of a tendency for exaggerated grain growth. Finally, some exercises. Questions. The diametral shrinkage is measured as 3.6%. Calculate the volume shrinkage, assuming the shrinkage is isotropic. What are the different states of water in an S-formed, nearly saturated product? Currently, digital printing machines are the most used in ceramic tile manufacturing. Explain how they work. Describe the functions of the bentonite, methylcellulose, and polyethylene glycol in the glaze batch. What are the factors that control adhesion of a film or coating? For a triaxial ceramic, build up a graphical representation, amount of phases versus temperature, for the description of development of phases during sintering. Describe an additive manufacturing technique applied to ceramic materials which include a sintering step. Build up a graph of concurrent grain growth against densification during sintering as a function of temperature. Compare field-assisted sintering to flash sintering. Explain how can sintering be carried out with lower environment impact. We have reached the end of our course. Thank you for your participation and congratulations on reaching this point.